Hello students, this is Dr. Ben. I'd like to take a few minutes to work through one of the homework problems out of Chapter 4. This was on the hand-graded homework Part 2, and this is problem number 11 that has to do with a sneeze. Kind of an interesting scenario. So we're given some information about what happens to the material that's emitted during a sneeze, and we're told that during the first part of the motion it accelerates from rest to a speed of 44 meters per second, and then it travels at a constant velocity for the rest of the way to the outside of the nose. And we're asked to find several of the kinematic quantities that have to do with this scenario. So I've already got a pictorial representation drawn on this sheet, and basically we need to have three different points of interest. So we have an initial point where the material starts. Point number 1 is where the acceleration stops, and then the final point is where the material leaves the nose. And we'll go ahead and set our coordinate system so that the origin is at the beginning of where the material starts, and so that's going to be initial position 0. The material starts from rest, and we'll start our clock at time equals 0. And then point number 1 is the end of the accelerating phase, and the acceleration between the initial point and point 1 is going to be called A1, and that's actually one of our unknowns. And then from point 1 to the final point, the material travels at a constant speed of 44 meters per second, and the position at the edge of the nose is 2.0 centimeters from the beginning spot. So we can use that pictorial representation to make our list of what we know and what we want to find. So we have our initial point, and the initial velocity and the initial time. And then at point 1 we know the position where the acceleration stops and the speed at that point. And then finally, at the final point, we were told that the edge of the nostrils are 2 centimeters away from the beginning point, and in the second part of the motion, the speed remains constant, so that should be V final, not V2, is going to be also 44 meters per second, and the acceleration is equal to 0 for that second part of the motion. So the first thing we want to do is to find the acceleration during the first part. Then we want to find out how long the material is actually in motion, so that's going to be the final time. And then we want to make a graph of the velocity versus time for this particular motion. Okay, so let's start by considering what happens from the initial point to point 1, and we're going to have constant acceleration for that particular phase. And if we want to find the acceleration without knowing anything about the time, the easiest way to do that would be to use the third kinematic equation that relates the velocities, the acceleration, and the displacement. So that would tell us that V1 squared equals V initial squared plus 2 times A1 times the quantity x1 minus x initial. And some of these terms are equal to 0, so the material starts out at rest, and we set our coordinate system so that the initial position was equal to 0. So we can simplify this expression and get V1 squared equals 2A1 times x1, and we could solve that for A1 to get V1 squared over 2 times x1. And the x1 is given as 0.25 centimeters. So if we convert that number into meters by dividing by 100 and compute this acceleration on our calculator, we get 387,200 meters per second squared. And that's a really large acceleration because this process occurs over such a small distance in time, a small distance. X, the value of x1 is only 0.25 centimeters. Okay, so now that we've got that acceleration, we could use that to find out the value of t1, because that will be helpful for the second part of the problem. So we can use either the first or the second kinematic equation to find t1. The second one would actually be easier, and so that would tell us that v1 equals v0, v initial plus a1 times t1 minus t initial. And again, marking down the terms that are equal to 0. The initial velocity is equal to 0, and the initial time is equal to 0. So we would get v1 equals a1 t1, or t1 equals v1 over a1. And if we do that on the calculator, we get 1.14 times 10 to the minus 4 seconds. So that's how long the accelerating part of this motion takes. All right, so moving on to the second part, where we would have point 1 going to the final point, that's going to be uniform motion. So the value of a2 is equal to 0. So really only the first kinematic equation would be helpful. So we would say that x final equals x1 plus v1 times t final minus t1 plus 1/2 a2 times t final minus t1 quantity squared. And the acceleration is equal to 0 for the second part of the motion, so that whole third term goes away. So I would want to rearrange this equation and solve it for the value of t final. So it's going to take a couple steps of algebra to isolate that variable. That should be the value of t final. All right, so we'll take x final minus x1 equals v1 times t final minus t1. Then I'll divide both sides of that equation by v1. So I have x final minus x1 divided by v1 equals t final minus t1. And then I simply have to add t1 to both sides. So I would get that t final equals t1 plus the quantity x final minus x1 divided by v1. And again, I've got to be careful here because the data is given in centimeters, so I have to convert that to meters by dividing by 100. So I get my calculator out and I come up with the answer 5.11 times 10 to the minus 4 seconds, or if I wanted to use metric prefixes, that would be 0.511 milliseconds. So that's 1/2 of 1,000th of a second. All right, so the last part then is to make a graph of the velocity in the x direction versus time. So I'll draw some axes here. And I'll put some labels on them. So the vertical axis will be v sub x, and the horizontal axis will be t. And so we have a constant acceleration for the first part, and then we have uniform motion for the second part. So on this graph, the constant acceleration will be represented by a diagonal line that has a constant slope, and then the uniform motion will be represented by a horizontal line, and so the graph is going to have that shape. Alright, so we figured out the acceleration, we figured out the time for the process to happen, and we drew a graph of the velocity versus time. There we have it.